So first of all, big thanks to our host, Bary, for putting this together. It's a wonderful conference, and I thank you humbly for it. I'm both honored and flattered to be here. Now, you will see the title is 74 years of chasing a 75-year-old concept. As I recently found out, it's not 74 years, it is actually 76 years, because apparently fictitious play, which is the process that I'm alluding to, already existed in a technical RAND report, which was classified from 49, and had to do with computing Nash equilibria and values of zero-sum games. And then it morphed into these two papers by Brown and by Julia Robinson here. And all these kind of initiated the hunt for a Nash equilibrium. All right. Now, my beginnings and my goals in this are much more humble. I'm not going to look at any possible dynamics, any universal results like that. My initial question is whether learning leads to a Nash equilibrium. No, we've found this out. Well, I would like to understand what the hell is going on and try to at least see with you. Now, there is one thing. I want to jump ahead to basically the end of my talk because I cannot resist, because Christos did such a wonderful job of also setting up this talk, so I cannot resist of moving up to one of the final slides, if I manage, okay, not this one, so, which has to do, and this is something that I would like you to keep in mind as we go along in the talk, which is basically the relation between preferences in the game and the actual output of the actual outcome of the dynamics. So here, what I'm showing is, well, I should actually zoom in, but believe me, I mean, even though the resolution is kind of low, all these things here, all these 4 games, these are 4 2x2x2 games, 2x2x2, yeah, and they're all the same game, except for one payoff to one strategy, except to the payoff to one strategy of a single player, all right? And I'm varying this continuously, okay? And I'm doing it in a way that does not change the preference graph of the game at all. So this little thing is that thing over here. This player gets a 0 in this game, he gets a 2 in this game, a 4 in this game, and a 6 in this game. And I want you to keep in mind that as this parameter changes, first of all, everything in the game changes. You start with a single equilibrium, which then actually morphs into 2. This is non-generic. This equilibrium actually splits into other 2. Then you get 5. Then you have a morphing. You have a catastrophe, and you have 3 that come in. And also, another thing that's going on is that the behavior of the dynamics, the replicator dynamics that we haven't yet seen written down, but this is what I'm showing here, changes completely. So they start by converging, everything starts converging to this phase. Then, as everything is going along, everything starts converging to that phase over there. All right, and this phase stops even containing an equilibrium. All right, so this is something that was also very annoying to me because in the beginning I also had this very noble goal of trying to relate this this very nice combinatorial structure to the dynamics of the game and try to draw conclusions. And then I had the fortune and misfortune of spending some time with Joseph. Fortune because you gain a lot of insights. Misfortune because, of course, he destroys everything conjectural that you may come up with. And so this is where I learned the hard way that this is something that is there are certain hard limits to what we can understand about the long-run behavior of the dynamics. So I'm going to try to take the complementary viewpoint to Christos' talk. I will not take a top-down. I will take a bottom-up and try to see what types of results we actually can obtain. There are going to be few. If you have a sort of if you have a hope for a universal convergence result saying we can do everything, drop that hope. This is not the talk for you, but I will show you at least what we do know. And I will start with some notation shenanigans. Okay, so first of all, everything is going to be about finite game, n players, finite set of actions per player, payoff functions defined in a similar way. What will be important are the pure payoffs and the pure payoff vectors, which collect basically the profile of payoffs at each vertex of the game, and also the mixed extension of all of that. So we have mixed strategies, we have mixed payoffs, and we have the corresponding mixed payoff vectors, which taken together make up the mixed extension of a game. All right, that's all for notation. If there are any questions, tell me to go back to this. All right, so I want to start with the title of my talk. I mean, 70-something years of chasing a Nash equilibrium, which is fictitious play. All right, now how did Brown and Robinson set it up? Very simple idea. Every player best responds to the empirical frequency of play of the other player. All right, now there are some caveats here. There are some subtle differences. First of all, just to be clear, what I mean by the empirical frequency in this case, in this particular case, I mean just the time average of the mixed strategies of a given player. There are only two. All right, and so every player is argmaxing against this strategy. This is what I'm doing here, which is just in this case because payoffs are linear and not multilinear in this case, everything is transparent, it goes out, so I'm basically argmaxing the sum of payoffs that I have accumulated up to this time, averaged out. Okay, now even here, there are some subtle differences. Fictitious play can be either simultaneous. This is actually the system that Julia Robinson studied, or alternating. This is the system that Brown suggested in his 51 paper, and even though in his 49 paper things were different. But anyway, things already start to change significantly when we pass to n-player games, because then I need to be very careful about what I mean when I'm saying that I am talking about the empirical frequency of play. All right, so there are two things here about how we aggregate strategies over time. One is we look at each player and we take the corresponding time average of their mixed strategies over time, okay, and we build a mixed strategy profile which contains time averages, or we look at every action profile, every n-tuple, how many times it has been played, and this is a correlated strategy, and this is the empirical frequency of action profiles, of play over action profiles. All right, so depending on which one we best respond to, we end up with two different versions of fictitious play. One is uncorrelated fictitious play, the other is correlated fictitious play. All right, both have been studied in the literature, and for both there are results, both convergence and non-convergence results known. For instance, we know we have convergence in zero-sum 2x2 potential and certain classes of supermodular games. We know that we don't have convergence in Shapley's game. Then Andrea and Joseph showed non-convergence in Jordan's matching pennies here, and Benaim and Hirsch did the same. Don't ask me to tell you which one of these papers is for which one of these versions. I don't remember, but what I do remember is that for the rest of the talk, I'm going to deal with this. Sorry? No, this isn't. Most of them. There are two. Sergio, go learn to count. Okay. All right. So, okay, I want to abstract away, however, because I want to look at this correlated view. This means just you take the sum of your payoffs and you somehow best respond to that. Okay, so this is the version that I want to look at. Now, oblivious of this whole fictitious play literature, which dates 50 years back, persons from computer science actually found out this algorithm, and they called it follow the leader. This was by Shai-Shalvas-Schwartz in his thesis work, where he started looking at this algorithm. Very simple idea in order to study no regret play. And the thing is, however, that this this is not a good learning rule. This is not a good learning rule, not because there are like super complicated games with pathologies that maybe things don't work. No, it fails very minimal very minimal desiderata, like the process leading to no regret. Okay, and so if you use this fictitious, correlated fictitious play in this very simple game, which I will let Peyton and Sergio tell me who came up with it, because I've seen both-sided for this game. I don't know. Sorry? Okay, Peyton, sorry. If you work these dynamics into this very simple game, you get positive regret. All right. So this is not a good way. This is not a good way to learn, even if you're trying to do something as minimal as guaranteeing no regret. All right. What you can do, at least to get rid of the no regret issue, is to smoothen this argmax, because this argmax introduces a lot of stability. It makes you, whenever it makes you best respond, and whenever there is some instability in your payoff vectors, it makes you shift from one strategy, from one pure strategy to the other, one ping pong between them, and this is very unstable. So what you can do is you can incentivize exploration by introducing a small penalty term, and this is something which is known as regularization. All right, and what this means is that instead of maximizing the sum of your payoffs, you are maximizing the sum of your payoffs minus a certain penalty term. However, now here comes an important change. Before, when I was maximizing the sum of my payoffs, I was solving a linear program. So whether I multiply it by a coefficient doesn't matter. Here, since I am adding this penalty term over here, it matters a lot whether I put a 1 over t, so whether I am best responding basically to the average payoff or to the aggregate payoffs. Okay, so these are two very different processes. One is smooth or stochastic fictitious play. I'm very happy that they both begin by S, so I can use the same acronym. The other is known in the regret and the online optimization literature as FTRL, follow the regularized leader. All right, and what we're going to do is, because smooth fictitious play has a property that it can never get, sorry? What? The perturbed. Yeah. But actually the perturbation idea goes back at least to those gentlemen over here, Fudenberg and Krebs, who actually established first the duality between doing a random perturbation in the payoffs or imposing this concave penalty or convex penalty, however you want to call it, on the deterministic side. Okay, so yeah, this smooth fictitious play has the property that it can never get sufficiently close. It is always bounded away from the boundary of the simplex of the strategy space. So if you have, for instance, a pure equilibrium, you will never converge even to a sufficiently small neighborhood of it. All right. So for this reason, I will not look at smooth fictitious play. I will look at FTRL type of dynamics. All right. And basically, if you want to view them as an iterative scheme, you can just take the sum and break it up into a state variable like that, and you have a very nice iterative scheme, which is also very well known and very well studied in optimization because it is related to the whole mirror descent family of algorithms, or in this particular formulation, the dual averaging by Nesterov in 2009. And actually, Nesterov was very playful with these dynamics, because he was introducing first. He was studying whether payoffs, or in his case, subgradients, enter the algorithm with a decreasing weight, or if they enter with the same weight, and then they are post-multiplied by some learning rate. And he showed that you can actually obtain different results depending on what you do. All right, for us, we are going to take this. We're going to look at a variable step size because it is more convenient for our purposes. But I just want you to have this very big puzzle of algorithms and methods, and how these ideas connect to in different literature and different fields. Okay. Now, two examples. First is if you do the standard Tikhonov ridge regularization, quadratic regularization, what you obtain is a discrete version of Friedman's projection dynamics. All right? So basically, you're just looking at the cumulation of your payoffs and you're projecting it in the Euclidean sense to the simplex, and that's what you play. And the other is the exponential weights algorithm, where you are aggregating your payoffs and you are then playing a strategy with probability which is exponentially proportional to its cumulated payoff over time. All right, this is the exponential weights, or if you want the multiplicative weights, this is what gives these are the dynamics that give in their limit the replicator dynamics. All right. And we're going to study this family, all this family of methods. All right, so just to revisit the model is like that. We have a finite game. Every player, at every point in time, discrete time, every player chooses a mixed strategy. Based on this mixed strategy, they choose a pure strategy. Based on this pure strategy, they get a payoff, and then they maybe get some feedback. If the world is very nice and the gods are good and the ancient and both old gods and the new are nice to us, maybe they get information about their mixed payoff vectors. Completely unrealistic, both from an observational and a computational viewpoint to have this type of information, but very nice in order to prove theorems and in order to obtain tractable results. They teach us a lot, so it is very useful. Okay, just because it's not realistic does not mean that it's useless. We're doing mathematics after all. So a slightly more realistic assumption is that players do not get to observe or somehow compute their full mixed payoff vectors, but they have some counterfactual information about the rewards of the actions that they did not play. So if yesterday I did not play A, but I played B, I know what I would have gotten if I had done that. All right, this is observation of pure payoff vectors. So that's a step towards being more realistic. And then, perhaps the most realistic one is when you only get to observe your own payoff, the payoff of what you played, and that's that, no other information. And if you go to a company like Crete or Google and you tell them that I would like to study this, they will tell you, no, you cannot even have this information because maybe there is a delay between you are playing and you're getting your payoff, or maybe you cannot even assign your payoff. You cannot even assign your payoff to the action that actually triggered that payoff, etc., etc., etc. We can play this game a lot, but these are the basic models that I want you to keep in mind. Okay, and okay. I think I don't need to show this example of what they actually look like. What I want to say is that there is a standard trick that you can use, so that if you only observe the payoff of the action that you played and no other information, then you can construct a proxy of your entire payoff vector, which is an unbiased estimator of your entire payoff vector. All right, and this is called the importance weighted estimator. And what it does is, given one single observation, so if you play action alpha and you get information V alpha for your reward, you divide that by the probability with which you chose this action, and then you put 0 everywhere else. This is a sparse estimator, and this is the importance weighted estimator. It has the very pleasant property that on expectation it gives you precisely the right payoff vector. It has the very bad property that its second moment or its variance actually blows up or if the probability with which you employ a given strategy is very small. Anyway, I want a sort of a unified way to treat all of these models at once. So what I will consider for the sequel is a sort of black box model for my mixed payoff vector. So I assume that somehow I either observe or am able to compute a stochastic vector, Vt hat, which is the correct mixed payoff vector plus some random noise plus some bias, some offset. All right, I'm not discounting this probability, and I will quantify the quality of my estimator based on these three statistics. How big is the bias? How big How large is the variance? How large is the second moment of my estimator? All right. And if you have mixed payoff vectors, of course, these are deterministic, so you have no variance, no bias, sorry, no noise. If you have the pure payoff vectors, you have no bias and constant variance. And if you have this payoff-based estimator, you have no bias. Why it is O of 0 and not 0, this is a question for the philosophers. But your variance actually grows inversely proportional to your mean, to the minimum of your payoff, of your probability, of your mixed strategy. All right. So that's regularized learning for you. This is the type of algorithms that we will consider. We will have this stimulus response scheme that I described in the beginning, where you aggregate your payoff information. And how do you get this payoff information? Via this black box model that we were discussing. All right. This is the general template. It has three basic ingredients. One is the step size over here, how much we weigh each payoff information as we go along. The actual black box model that is providing us payoff information, and then the regularizer, which determines actually determines the shape of the dynamics. All right. So just to give you an idea of what this template includes and does not include, in terms of things that it does include, it includes all vanilla forward mirror methods, so exponential weights, lazy projection dynamics, etc., etc. It includes all the banded payoff the banded or payoff-based methods that we use in online learning, like EXP3, Tally-Synth, the broad algorithm, and stuff like that. And it also includes extrapolation methods, like for those of you that are familiar with them, like extra gradient, mirror prox, optimistic methods, and I see George here, so implicit methods like clairvoyant and stuff like that. So I will show you an example. What it does not include, and I want to be absolutely clear about this, it does not include any regret matching type of rules. It does not include any trial and error type of rules or any calibration type of rules, all that. These are beyond this framework. So what I'm going to say applies to this wide family of methods, but these have completely different guarantees and outcomes. All right. Okay. So, just to, well, I'm running a bit late, so I will rush through this. If you have a question about how you can include any of these methods, if you're familiar with these methods and you would like to see how you can include it in this template, I had here a bunch of examples showing how the black box model for it actually can account for each method. I will speed run through this, and if you want to talk about this, we can take it offline, because I guess the principle is more or less clear. All right. Instead, what I want to do is, in the last 10, how much?
10 if you want 5 for questions.
Yes. Okay. So 10. In the next 10 minutes, I want to give you an idea about what happens, what we can expect from different instantiations of these dynamics, which instantiations give different results, which gives the same, differences, similarities, qualitative, quantitative, stuff like that. All right. So I'm going to start like Brown and Robinson with zero-sum games. All right. And I'm going to run, what I'm showing here is 3 things. I'm showing the continuous time limit of the dynamics. So these I'm plotting here the exponential weight dynamics. Okay, so entropic regularization, if you want, which in the continuous time limit is just the replicator dynamics. I'm continuing on Christos' tradition, and I'm not putting them on the board. I let you imagine them. The equation, I mean. I'm also plotting here the vanilla, the standard exponential weight algorithm, and also the optimistic version of this algorithm, okay? Now, this is something which is by now well known. These things were discovered around 6, 7, 8 years ago. Well, at least this. Here, in the continuous time limit, the dynamics are what we say Poincaré recurrent. Here they are actually periodic. Poincaré recurrent means that they are quasi-periodic, meaning that they return infinitely close to where they started infinitely many times. All right, so we have this very nice periodic behavior. Very nice. Not from a learning viewpoint. From a learning viewpoint, this is horrible, because this means that you learned absolutely nothing. You came back to where you started. This is worse than having an attractor which is not in Nash equilibrium. If you have an attractor which is not in Nash equilibrium, at least you learned something. Is this something meaningful? Depends who you ask. But if you just get back to where you started, then definitely you haven't learned anything. All right. But this is what happened with continuous time. If you are doing exponential weights, okay, so this is the standard forward mirror interpretation. Implementation of the dynamics, then you go out. You start in the simplex, you go out to the boundary of the simplex, and you end up cycling around the simplex. If you do this optimistic version, this extrapolation-based version of the exponential weight dynamics, you basically, it is as if you were running the dynamics almost backward, and you end up converging to a Nash equilibrium. All right, so this is something which is makes us like the optimistic version very much, because in...
Can you repeat what optimistic is, now that you understand that it's important?
Yes. So optimistic is this algorithm where you are instead of adding the payoff that you actually obtain, you add the payoff that you had obtained the previous round another time. You take an extra step forward, you sample your payoffs there, you go back, and you use the payoff information that you got there in order to make the update. It is very complicated the way that I stated in words. If you want offline, I can draw you a picture, and it is going to be much simpler.
It's like a forward algorithm it's a counterpart of the forward algorithm for the linear online.
It is a counterpart of the forward-backward-forward algorithm, if you want. Okay? Because it has 2 forward steps and 1 backward step. It's Tseng's algorithm, if you're familiar. But with words, it's horrible. If I had a blackboard, it would be very simple. And so just let me do this offline. Now, this is something that we like. All right. However, this is something that is true in the deterministic world. This is something which holds with observation of the full deterministic mixed payoff vectors. If I have stochasticity, even if I have a modicum of stochasticity, this image is destroyed. All right, and you see that the exponential weights, the forward, the standard, the vanilla implementation, and this sophisticated optimistic implementation, they all give the same thing, a big, beautiful mess. And in particular, it is very difficult to say something about the stochastic properties and the recurrence properties of these stochastic dynamics, but you can't say that they do not converge and they do not concentrate measure anywhere in the interior of the state space. I have 5 for questions, right? Yes, good. All right, so this is the first thing that I want you, a first important takeaway, that the benefits of all these extrapolation methods that we like a lot are extremely fragile. All right, and if you are in a less pristine world than the fully deterministic one, they all go out the window. Second thing, let's try another game, Battle of the Sexes, like coordination-like game. Here the difference is that the replicator dynamics have what Christos lovingly set up for me, a lot of attractors. All right, so you have Nash equilibria, 2 Nash equilibria here that are attractors, and 1 which is unstable. All right, and then you see that in the discrete time, fully deterministic world, you have basically the same picture as you do in the continuous time world, both with the vanilla and the optimistic implementation. And importantly, even if you have stochasticity, you still have the same behavior. All right, so this is what tells you this, for me, is another reason for which the attractors of the replicator dynamics or of the continuous time dynamics are so important from a learning viewpoint, because they are robust. In contrast to recurrent behavior or chain recurrent systems like zero-sum games, which are not at all robust, they are completely destroyed when stochasticity enters. These are robust, okay? And this is the theorem to that in that regard. If you are in the stochastic world of these regularized learning schemes, all right, you say that a set is stochastically stable if whenever you start close enough to it, you remain close enough to it with arbitrarily high probability, and you say that it is also stochastically attracting if whenever you start close to it, you converge to it with arbitrarily high probability. And if you have both, you say that it is stochastically asymptotically stable. All right. And what is nice is that here there are some parameters that have to do with the statistics of the black box model. All right, but the important thing, I mean, I can walk you through the various parameter choices, but the important thing to keep in mind is that for all these examples that we talked about, these are all satisfied. Then, if you have an attractor of the continuous time dynamics, then this is also an attractor of the discrete time dynamics with any black box model satisfying these guarantees for any regularizer, and the step size can actually be constant in this case. All right. So this is what motivates the question. I mean, for me as well, from a different viewpoint, not from a complexity viewpoint, but from an operational learning viewpoint, how can we characterize the attractors of the continuous time dynamics? Christos has shown that it is very difficult. So of course my results are going to be very poor. First poor result that I have, Pullman's result, concerns point-wise attractors. Which are the point-wise attractors? Which are the points that these FTRL algorithms can be attracted to? And here, the important thing to keep in mind is this property 3, that the only point-wise attractors of this entire class of dynamics are strict equilibria, and these are precisely the point-wise attractors. All right. You can say more if you have a congestion or a potential game, but this is the characterization that at least I find more interesting, because it builds on a series of earlier results on the replicator dynamics by Joseph and Karl and Jürgen Weibel and many others. All right. I will skip this for the rate of convergence because I realize I have 1 minute left. And what I want to show you is at least some results about set-wise attractors of the replicator dynamics. All right. Here things are, again, we can say some things, not a lot of things, but at least what we can say is that if we have a span of pure strategies, so think of a subgame, and we want to identify which subgames are attractors of the dynamics. All right. What you can show here, and this is a generalization of a result by Jürgen Weibel and Klaus Ritzberger, that a span of pure strategies is stochastically asymptotically stable if and only if it is closed under better replies. What does this mean? It means that if you take the preference graph, all arrows, there are no outgoing arrows from that face. All right. Importantly, however, this is a result which concerns subgames, faces. We cannot extend this to more general club sets of the preference graph. This is the example I wanted to show here. But at least in this, since Christos ended with a conjecture, I cannot resist the temptation to do the same. And if I am giving up hope to have a complete structural characterization of the attractors of the replicator dynamics and hence of this regularized class of learning schemes, that would be to at least pinpoint their location. And my conjecture is that any asymptotically stable limit set of the replicator dynamics or these regularized learning dynamics has to live on the boundary. All right, I have not been able to prove this. Joseph, for now, has not.
Which dynamics?
Replicator dynamics or any regularized learning dynamics. Yeah. Joseph so far hasn't been able to. Hasn't been able to disprove it. Hasn't disproved it, most likely because he's hiking in the Austrian Alps. But at least for now, this conjecture stands. So yeah, if anyone has any ideas, I will be very, very happy. All right, thank you.
On this very last conjecture, from the way you put it, it looks like it depends a lot on the dynamics you consider. But it also depends a lot on the very simple fact that the payoffs are multilinear. Just as you get rid of that, you might easily have attractors in the interiors.
Of course, this has to do with finite
games, sure.
You go to symmetric matching in two-player games, bye-bye, you have Zim and you have, it does not hold.
So is it not surprising that this simple property of multilinearity upon this complex framework of dynamics gives this consequence?
I don't know how to answer this question. I mean, they have a lot of, these things have, these dynamical systems on multilinear games, they have a lot of structure. They have a lot of topologically non-trivial properties, including conservation of volume in the dual space, et cetera, et cetera. So if you put all this together, for me, it's a toss-up whether it is enough structure or not. But these are very highly structured. This is a very highly structured system, so I would not immediately discount it. Yes?
Something we did not consider, you said regret matching and other things. Do they behave differently in respect to this conjecture?
I don't know.
Or you don't know anything about them?
I don't know. Yeah? Sorry, I took the role of chair. I didn't mean to.
With this conjecture, do you mean, are you referring specifically to minimal asymptotically stable limit sets? I mean, you're not...
Limit sets.
Okay,
limit sets. Sets of limit points.
Yeah.
So not attractors, because any attractor, if you take a backward push of within the basin, this is still an attractor. Of course, I don't mean that, as I assume that Christos did not mean it either. But yeah, sets of limit points.
Thank you, Panayotis. Since all real-life games...
I have my eye on you. Be careful what you ask.
Since all real-life games are extensive form games, can you say something about...
I beg to differ with that. Huh? I beg to differ with that.
You disagree or you agree?
I completely disagree.
Okay. So can you give your comment?
Congestion game. Congestion game. A routing game, if you want. Yes. Yes.
So let's say most of economic model, or many, at least there are many games that are extensive form. So can you say something about your tools for extensive games?
Let's look at extensive form. We'll get it.
All right. So first of all, I never said generic here. Okay. I never said generic. The notion of being, the notion of having a club set, etc. These also apply in the case where we have payoff ties. Of course, strict equilibria would never exist in such a generic. I mean, would never exist. Depends on how you define generic game. Exactly. Depends on. I mean, generic is a very dangerous word, so I wouldn't dare say. But yes, I think that Sergio gave the right response. That you want to look at extensive form games, let's look at extensive form games.
Okay. No, but my point is, if you learn in extensive form game, you want to learn on the behavioral space, not on the.
I agree, space. Which changes this framework completely, because exactly because you want to learn on behavioral strategies, so you no longer have this structure. You no longer have necessarily this type of regularization, etc. For me, super interesting direction. And people, there are even in in the previous, in the last morning talk by Vincent, I mean the group in Carnegie Mellon by Thomas Anton has done a lot of very formidable work on extensive form games. Other works by Gabriele Farina, who is now at MIT. There are lots of things that are being found out as we speak, but a completely different question.
Okay, thanks again. Let's
yeah.
finish.